Morning Year 10, this is Mr. K going through your Year 10 mock. So, to start off, make sure your name's on it. First up, place a cross in the diagram that represents hydrogen gas. You should have underlined hydrogen gas, circled the gas, and that is this box right here. So that's for 1 mark. Next, the particle furthest from the center of each atom. Well, this is an electron in this diagram, it's this one right here. Okay, and so it should be A, an electron. A slightly more interesting question. The particle represented in Y but not in X, so that is clearly this grey one here, okay, which I've labelled neutron. Now the reason why you know it's a neutron is because the nucleus has to contain both protons and neutrons, and the X has a black circle, the Y has a black circle, the difference being the grey circle. Now given that every atom has to contain protons, the only plausible process of elimination answer that the grey one could be is the neutron. Yeah? Some atoms don't necessarily have to have a neutron, hydrogen being a classic example. So both atoms are neutral because they have the same number of electrons and protons. Protons have a +1 charge, electrons a -1. So when they're the same, it obviously doesn't have a charge. Neutrons, you should remember, are neutral, 0 charge, hence why they get their name neutron. Next up, notice the difference here between the 16 and the 18, but the 8 stay the same. So these atoms of oxygen, they're called isotopes because they've got a different atomic number, because their atomic numbers are the same, so the 8 is the same, but their mass numbers, so the 16 to the 18 is different. Okay, and in fact the oxygen with 18 has 2 extra neutrons for those of you that were interested. Okay, next diagram. Now this got reasonably poorly answered by your year, so just to go through a few things. First of all, you've got the reactants on the left hand side, okay, of this diagram, and on the right hand side we've got our products, which is actually just oxygen. Water's not really involved here. Water's just acting as a way to collect the gas. Okay, so water's not involved. Now the first question is asking, state the mistake in the labeling of the diagram. Now you should know that magnesium oxide is actually a solid and hydrogen peroxide is a liquid. Therefore these two are incorrectly labelled. Okay, it was a little bit confusing in that there's a liquid in this container. Now this liquid is actually because the diagram is halfway through the reaction. Okay, so the reaction has already been allowed to proceed a little bit, so some hydrogen peroxide has been added down onto the magnesium oxide and the gas has been collected. Okay, so that's why you've got some oxygen already present and some liquid in here. It's not because it started there. So anyway, the answer to this, obviously the reactants labelled the wrong way around, or you could have said magnesium oxide and hydrogen peroxide incorrectly labelled. Identify the piece of apparatus missing from the diagram. So this is a bung or a cork. Let's put this in blue and it's going to slot right in here. Okay, so this is the bung which is missing. You could have had stopper but ignored plug. State why this piece of apparatus is necessary. Obviously it's to prevent oxygen gas from escaping, and oxygen wasn't essential here. You didn't actually have to have the word oxygen, so a gas would escape, or the gas couldn't be collected, because obviously if this bung wasn't here, the gas could just squeeze past this area here, squeeze past those tubes and escape and not go through the tube. So you want the bung there. So question 3 asks, first of all, complete the equation by inserting state symbols. Now we're adding some sulfuric acid to a beaker containing some calcium chloride solution and watching a precipitate of calcium sulfate form. Precipitate tells you that this must be a solid, okay, and this is diluted, which means it's in H2O, and this is a solution, which also means it's in H2O. These tell you, all the answers are in the question, that calcium chloride must be aqueous, okay, because it's in solution. H2SO4 must be aqueous because it's diluted, and CaSO4 must be a solid because it's formed a precipitate of calcium sulfate, and hydrochloric acid is obviously a solution as well, therefore it must be aqueous. AQ stands for aqueous, meaning dissolved in H2O, and S stands for solid, meaning solid. Draw a diagram to show the assembly for filtration. So what you wanted was the filter paper in the funnel, that's 1 mark, and then the rest of the diagram correct for the second mark, which is essentially drawing the funnel in a conical flask. Nice easy 2 marks there. Identify the arm responsible for this colour. So you've got a brick red colour. If you remember your flame tests, that's a calcium 2+ arm, and you did need the charge for the mark, okay, 2+. Suggest why this ion is present in the filtrate. So the filtrate is the liquid, obviously, that has gone through the funnel, yeah, so whatever passes through here, this is the filtrate, okay. Now why is there an ion present? Well, it's because the calcium sulfate is actually ever so slightly or partially soluble. So although you are forming solid, I'm going to draw dots here to represent it, you're going to form solid calcium sulfate, okay, but some of it can dissolve and head into the dissolve into the water and therefore pass through the filter paper and into the filtrate. Now if you didn't get that, you could have also said that it contains unreacted or excess calcium chloride or calcium ions, and so essentially because you had CaCl2 plus H2SO4, if this was in excess, you would have some left over, and this is soluble, calcium chloride, so calcium chloride can easily pass through into the filtrate. It can get through that filter paper because it is soluble. Question 4. A teacher uses this apparatus to show the reaction between ammonia gas and hydrogen chloride. So this is showing ammonia is soaked here and hydrochloric acid soaked here. So I'm actually just going to draw those on the next diagram. Okay, this is ammonia and this is HCl on this diagram. Now the white solid is slightly over towards the HCl. This means that the NH3 travels further. Okay, so which process occurs when the gas particles move along the tube? You should have got this as diffusion, bumping randomly into each other and distributing evenly, or randomly actually, sorry, across the tube. Explain how the diagram shows which gas moves more quickly during the experiment. So which gas, so you need to identify the gas, which in this case is ammonia. Okay, so ammonia has moved more quickly because it has travelled further. If this is the white solid, so this is the white solid, yeah, and it's over towards the HCl, ammonia has travelled further, so therefore the ammonia is less dense and essentially is able to diffuse a lot quicker. So that was only worth 1 mark. You need ammonia and it travels further. Next up, a teacher tests a sample of ammonium chloride solution. Suggest the identity of X. So he adds X, warm mixture, and tests the gas given off. Now, you should know the test for ammonium ions from year 9. So if you add sodium hydroxide and warm it, you will get ammonia gas. This is the one which kind of smells pretty bad. It smells like urine or cat pee. If ever you've left your cat in your house over a holiday or a weekend and it's pissed everywhere. So that's ammonia, and the colour of the litmus paper is blue, because your red litmus would turn blue since ammonia NH3 is alkaline or basic. Why does she add dilute nitric acid? This is quite an interesting one. Very few people got it right, but the reasoning is to remove carbonate or sulfite ions. Or you could have said to prevent other ions interfering, or you could have also said to prevent other precipitates from forming, and that was just worth 1 mark. Suggest the identity of solution Y in the white precipitate. So this is a test essentially for halide ions, because chloride is a halide ion. So it's nitric acid, and this Y is silver nitrate. Yeah. So the precipitate that you therefore form is silver chloride, which is white. You've got chloride ions, and it's told you that in the question. Therefore, adding that to the silver nitrate forms silver chloride. You could have put the word or the symbol here, and again, word or the symbol here. If you put both, they both need to be correct. Next up, question 5. Question 5. What's going on? Oh, there we go. I've made a table for this to make it quite simple. So, instead of masses in this question, we're given percentages. So let's just underline them so they're clear. Methane is used in many countries as a fuel. One of this substance is compound X, which has a composition by mass. Now, the masses, obviously being, the percentages, if you add them up, they come to 100%. Okay, so although you're not given the mass, if you had 100 grams, then within that 100 grams, you'd have 53.3 grams of carbon, 11.1 grams of hydrogen, and 35.6 grams of sulfur. So the percentage is actually more useful, and you just treat the percentage like a mass, yeah? And the total mass being 100 grams, given that 100%. So 53.3, 11.1, and 35.6 should all add up to 100. Anyway, 53.3, we're going to use that percentage as grams instead, 11.1 and 35.6 grams. And then, given that moles equals mass divided by mR, I've put AR here because it's technically more correct. This isn't, this is just the atomic number, sorry, the atomic mass, not the molecular mass because it's not a molecule. Anyway, so it's 53.3 divided by 12, 11.1 divided by 1, and 35.6 divided by 32. You get these from the periodic table, and that gives you these numbers, 4.4, 11.1, and 1.1. Now, if you got this answer here, you would have got mark 1. So you needed each one of these that I'm circling for the mark 1. For mark 2, let's do that in blue. You then needed to do this, divide by the smallest number of moles. Now 1.1 is the smallest number, so we're going to divide 4.4 by 1.1, and that gives you 4. 11.1 divided by 1.1, and that gives you 10. And 1.1 divided by 1.1 equals 1. This divide by the smallest ratio is essentially making sulfur 1 and telling you the ratio of everything else compared with sulfur. Given that sulfur had the smallest ratio, this 1.1 is a bit awkward, so let's change it to 1, and to do that we just divide it by itself. That makes it 1, and to keep everything fair we need to divide all of them by 1.1 if we did it to sulfur, so that gives you 10 and 4. So finally, for the third mark is C for H10S, and that's mark 3. The 4, 10 and the 1 were the mark 2. Yeah, a lot of people here rounded the moles. Don't do that because they actually set it up quite nicely to get these nice numbers, 4, 10 and 1. Okay, the relative formula mass of X is 90. What's the molecular formula of X? Well, if you, first of all, let's work out the MR of this. So the MR of this is 12 times 4 plus 10 times 1 plus 32 times 1, which equals 90, which is what is said in the question. Therefore, the ratio must stay the same, so it's exactly the same answer. Okay, no change in ratio. So that's just C4H10S. And question 6, dot and cross diagrams. Draw a dot and cross diagram for the ions in lithium nitride. So 1 mark is for both electronic diagrams, correct. Now remember, you need to draw the outer shell. Now obviously lithium did have an electron here like this, but you've lost that electron, so you remove that shell, leaving behind its new outer shell, which is what was its inner shell, which has 2. So although you've removed this shell, don't just leave this shell empty. Yeah, you could, if you wanted to, draw that and have the electron lost, but you need to draw this new shell, the inner shell of electrons. Not so important on nitrogen because you've got the outer shell. Okay, I would suggest that you draw all shells, so you're not left in confusion as to whether to draw the inner shells or not. Mark 2, both charges are correct, so you needed a plus and a 3 minus, and the ratios. So this is mark 3. Okay, the ratio is 3 lithium. You could have also put a 3 here, that would also be fine. I wouldn't be bothered. But yeah, as long as you've said there's 3 lithium to 1 nitrogen. The chemical equation for the reaction between lithium and oxygen is Li plus N2 goes to form Li3 plus N. 1 mark for the correct formula, and mark 2 is for balancing. Okay, so what is in blue is for balancing. You should realize, given that this is a plus charge and nitrogen is a 3 minus charge, they therefore, to be chemically neutral, we need 3 lithium to 1 nitrogen. Okay, 3 lithium ion to 1 nitrogen ions. So yeah, so this chemical formula is Li3 and N, and then you just have to balance the rest. Nitrogen is diatomic, so it goes around with a nice triple bond like this. Okay, so it has to be N2. Diatomic meaning 2 within the molecule. Solid lithium nitride conducts electricity is used in batteries. Why would you expect solid lithium nitride not to conduct electricity? And it's a solid and it's a ionic compound, and therefore the ions cannot move, or the ions are not free to move. Reasoning, ionic compounds only conduct when molten or in solution. You just needed one of those for the mark. Okay. Question 7. Question 7. So the diagram shows the electronic configuration of the atoms of magnesium and chlorine. Now, they've been nice to you and actually given you these diagrams already, which you're going to use later on. But anyway, describe how magnesium atoms and chlorine atoms form magnesium ions and chloride ions. So these are atoms, and how do they form their ions? And the word here is describe. Okay, so 1 mark was for electron transfer, the second mark is for magnesium atoms lose 2 electrons, and the third is for electron atoms gain electrons. So as a model answer, I would put magnesium loses 2 electrons to chlorine, which each gain 1 electron. Okay, so 2 chlorine needed to receive the 2 electrons from magnesium. Okay, here you're clearly saying magnesium loses 2, you're clearly saying chlorine gains 1, and you're saying that magnesium loses them to chlorine, so that you're saying the transfer. Yeah, so magnesium loses them to chlorine. Draw dot and cross diagrams. So they should look like this. Very simply, this is going to lose its outer shell, and this is going to, the chlorine is going to gain an electron here. Okay, so you just needed to show that. Chlorine has gained this electron, magnesium has lost this empty outer shell, okay, leaving it as a 2+ charge, and chlorine as a negative charge. So 1 mark was for the correct configuration of magnesium, 1 was for the correct configuration of chlorine, and the 3rd mark was for the correct charges of +2 and negative. Okay, a little bit more description there if you need it, so you can pause the video if you're unsure. Moving on, your oxygen has 1, 2, 3, 4, 5, 6 electrons. This oxygen also has 6. 1, 2, 3, 4, 5, 6, and our carbon has 4 electrons. 1, 2, 3, 4. The key thing here, so mark 1 was to show 4 electrons in bonding. Okay, 4 electrons in bonding, and then mark 2 was for everything else. So you needed to remember these extra electrons on oxygen. So describe the structure of the bonding in indium. Now, indium is in a metal in group 3. Describe the structure and bonding. So essentially what it's asking is describe the structure and bonding of metallic bonding. And that is positive ions surrounded by a sea of delocalized electrons arranged in a nice giant lattice. So to put a model answer, positive cat ions of indium are surrounded by a sea of delocalized electrons and arranged in a regular giant lattice. Okay, that would be the model answer that I put, and you've covered the 3 marking points. Explain why indium is malleable. You've got layers of positive ions which can slide over each other. Yeah, model answer being layers of positive ions which can slide over each other. To put that in a diagram form, your ions look like this, okay, and your electrons, sea of delocalized electrons, look like this. These are supposed to be crosses. Okay, now it's malleable because if you were to push this section here, okay, these atoms would go this way, all these atoms would stay stationary, and so you'd get a nice shift essentially, and you'd have the atoms arranged like this. Yeah, so it's quite easy to hammer into shape because you can push this whole row over the top of this one. Question 8. Name the type of bonding that exists between carbon atoms in all 3 structures. Covalent bonding, they're sharing electrons. Explain why diamond has a very high melting point. There are 4 marking points for this. So a model answer that I would put is diamond is arranged in a giant lattice with 4, actually let's change the number 4, let's many strong covalent bonds to break these strong bonds. Lots of energy is needed. Okay, so you're clearly saying, well, diamond has loads and loads of these really strong covalent bonds, these really, the really strong covalent bonds, and you can see that they're all attached to each other. There's lots of them all arranged in this nice lattice. So to break it, you've got to break apart every single one of these, which is going to require a lot of energy. A quick little addition to question B that I wanted to add was this last statement, or the last Mark 2 and Mark 3. You pretty much are going to add those every time a question is talking about why it has a high melting or boiling point. Okay, just remember these 2 last statements. Okay, always add. Yeah, even if it's ionic bonding, why something has an ionic bond has a very high melting point, you can also add those 2 statements. Okay, so this sentence here at the end, to break these strong bonds, lots of energy is needed. Remember. And if it's talking about a high melting or boiling point, always add that statement. You're not specifying the bonds here, so strong bonds could be ionic or could be covalent. So remember that one sentence and you can apply it to both, and that's worth 2 marks. Okay. Okay. Next question. Fluorine is a simple molecular structure. Explain why it has a low melting point. Fluorine, this is one molecule of it. Okay, so you could have another one next to it, and in between them there aren't covalent bonds. Yeah, unlike diamond, diamond is going to keep repeating like this until you get to the very edge of the diamond crystal. But fullerenes, you've got one of these balls and then you'll have another fullerene molecule next to it. Those two molecules only interact by these weak forces, okay, or intermolecular forces I should say. Yeah. So you don't have to break covalent bonds if I want to separate, say, this ball A from ball B. If I want to pull them apart in opposite directions, I just need to break these weak forces. So quite simply, a model answer would be fullerene has weak intermolecular forces, little energy needed to break them. Okay, so you're saying intermolecular forces. We should add here between molecules, that is important. Okay. So little energy is needed to break them. Question C. Now this was quite a tricksy one, as it were. Theory A is actually what happens with graphite, but the question asks which theory is supported by evidence. Okay, so they're trying to make you read the table and use the information rather than information you already knew. So the table shows the ability of graphite to act as a lubricant, and as you can see, as it goes into space, it gets less or worse as a lubricant. Okay, so on the Earth's surface there is plenty of air. Lots of air here, and outer space, no air. Okay, so the thing which is changing is the amount of air in between the molecules as you go into space. Now, if you went into space, the air disappears and the layers would then sit on top of each other and there would be no gas. So therefore, this data supports theory B. Gas molecules are trapped between the layers, allowing the layers to slide over one another. Because outer space, like I'll say, has, like I said before, has no air. So if you take it into outer space, that air, or these gas molecules, are going to go. Therefore the layers will sit on top of each other and won't be able to slide. So the fact it's getting worse as the air disappears means it must be theory B. Okay, so theory B and the reasoning, there's fewer gas molecules in space, or there's less gas in space, or space is a vacuum. Finally, question 9, the lovely mole question. So calculate the amount in moles of NaOH in 100 grams of sodium hydroxide. So I want you, first of all, underline all the key terms. So we've got 10 grams of solid sodium hydroxide in 100 centimeters cubed of water. So calculate moles. Well, you're given a mass, and moles equals mass over mR. Yeah, you should know that equation. So it asks you for moles, and you're given a mass in grams. Therefore, the thing that's missing from this equation is the mR. So the mR of NaOH, well, sodium is 23, oxygen is 16, and hydrogen is 1. These numbers are again, look at the periodic table. Okay, they're from the periodic table. Anyway, that equals 40, and that's your first mark. You then just had to take that 10 grams and divide it by 40 for the second mark, which gives you moles of 0.25. Now you had to calculate the concentration Well, concentration is moles over volume. You already have the moles from the previous question. Okay, that's there. So that's 0.25. And the volume, if you read back in your question, was a nice 250. Let's highlight that in blue. Okay, so that's going to be our volume. And notice though the units, decimeters cubed, and our units for the volume there were given in centimeters cubed, so you needed to divide the centimeters cubed by 1,000 so that it puts it into decimeters cubed, and that gives you 0.25 divided by 0.25, which gives you 1. Okay, now you could also, I drew this equation in a weird way, I thought it would make the most sense, but you can rearrange this equation actually to like that, 0.25 divided by 250 times 1,000. Yeah, this is the same as taking 1,000 up here. Okay, so 0.25 divided by 250 times 1,000, and it still gives you your final answer of 1. Okay, feel free to stop and play the video. Thank you, and all the best, Mr. K.